Hello everybody, this is Saif Habashi, an electrical engineering student at Cairo University. Let's go without too much introductions. In this video we are discussing inductors for power supplies, because to understand power supplies you need to look at inductors from a little bit different perspective to understand how we analyze switching power supplies. So, inductors. Well, we can discuss inductors from the magnetics perspective. You know, how a cycloid, for example, like this one, with some wound wire like this, and how to calculate the inductance of this coil and so on. But we do not care about this for now. We can discuss this, and this is really important for power electronics, but that's not what we are focusing. That's not our focus right now. Our focus is to study the lumped element model of the inductor, which is this simple, nice, cool element. Let's say we connected it to some circuitry, right? And this circuitry is injecting some current into this inductor and producing some voltage across it. So, what is the relation between the voltage across this inductor and the current going inside it? Well, the inductor says, look, my voltage is L, or my inductance value, multiplied by the rate of change of the current that is going inside me. Okay, what does this mean, Mr. Inductor? He says that this means a lot of things. The first thing, we can say that this voltage cannot be infinite. So this rate of change of current can be infinite, which means that the current inside this inductor cannot go from a certain value to another one instantly, like this. Inductor current cannot be 0, 0, 0, and suddenly at a certain time becomes another value, like this. This cannot happen. Why? This is the inductor current, because this would mean that the voltage producing this current has to be like this. You know, the voltage was 0, 0, 0, 0, and suddenly it went really high to infinity and went down again in no time. And no such a thing. Right. So there is no such thing. This voltage cannot be infinite, which means that this current cannot change suddenly. And the higher the inductance, the strong, or the harder this current can change fast, or the more resistant this inductor to its current changing faster. Right? This is the first rule. So rule number 1, inductor current cannot change instantly. Right? Second thing we can deduce is that why not connect this inductor to some voltage source like this? What's the problem of having this inductor connected like this? Where is the problem? Let's say we have a switch here, and we decided to close this switch at t equals to 0. Let's say this inductor has 1 Henry, and this voltage is 5 volts, for example. So this switch, when this switch is closed, some current would flow, right? And some voltage would be across this inductor. The voltage is 5 volts, obviously. The current would be, since VL equals L di by dt, and V equals 5 volts, this means that the current across the inductor is equal to, this L is equal to 1, right? So the current inside this inductor will be 5 times t plus some constant, which is the initial value of current. We will say that it is equal to 0. So this inductor current, if we want to plot it, it will look like this, just increasing linear current, ramping. This is IL, this is T. At T equal to 1 second, this inductor current will reach 5 amps. This is really bad. Really bad. And don't do this at home. Don't do this at home. Right? So, what can we do to limit this happening? Because we want to use it in circuits. Well, one way is we can put a resistance at its way, but this is not the best thing to do, since we don't want power losses. Well, another thing is we can do this. This energy is getting stored inside this inductor. There is some current flowing through this inductor and some voltage across it, so there is some power is getting inside this inductor, which is V times I. And obviously this power is increasing, but this power is not getting dissipated or going out as heat. It's getting stored inside this inductor as magnetic energy. We don't care about magnetic fields right now, but it is stored as current. Because another example of connecting this inductor, maybe, well, let's get some voltage source and a switch like this, and a circuit like this, and the inductor is here like this. And we will switch this guy here, also 1 Henry. When we switch it like this, we are going to have a circuit like the previous one, and the current will be increasing just as in the previous example, like this, right? For, let's say, 1, 2, so there it is, 2 seconds. Let's say we kept it 2 seconds right here, and we switched it again to this side. When we switch it here, right, this is for the circuit when it is like this, right, 5 volts and 1 Henry. When the circuit is like this, but there was initial current inside the inductor, we kept it for 2 seconds, so the inductor current would ramp up to 5 volts and then 10 volts, right? At this time, from after 2 seconds, after another 2 seconds, the um, the voltage across the inductor is zero. Now the L equals zero, which means that the I by the T is also zero. So the current will stay at its value like this. And we actually created a current source that is closed on itself. This is exactly equal to this. 10 amps. Oops, I'm really, really sorry. These are amps. Okay. Cool. Right now, cool. So an inductor connected to some voltage, its current starts ramping up, and if we switch this voltage to zero on the inductor, we make the inductor voltage equal to zero, its current will be kept constant. Unless there is some resistance in this way, it will dissipate this current, but this is not our case. We assume ideal things. So there is no resistance in this way, so the inductor current will be kept constant. If there is some resistance, actually it would not be really constant, it would decay like this. It would actually go like this. But it would decay really, really slow if the resistance is really, really small. So we don't care. So what happens if we keep switching between these two guys? We switched. This graph is for a case where we switched to the 5 volts, kept the inductor's current ramping for some time, then we switch to the 0 volts, and the inductor current will be kept constant. What if we kept switching? What will happen? Another example. This is, some voltage right here, and this voltage is square wave across the inductor. What does a square wave, oscillating between 0 and 5 volts, right? So this is the inductor voltage. The L is oscillating between 0 and 1. So let's make it like this. 0 and 5 volts. Right? This is 1 second, 2 seconds, 3 seconds, 4 seconds. Right? So the inductor current would look like this. I want to get to something. Bear with me. I know this looks trivial, but I want to get to something. So the inductor current here would look like this. 5 volts, so 1 times the I by the T equals 5. So the I by the T equals 5 amps per second. So you'll be increasing at a rate 5 amps per second. So after the first second, you'll get to 5 amps. 0 voltage means the voltage is constant. 5 volt voltage means the voltage is increasing, constant and increasing, and so on. So let's get it here. So periodically this guy is going to keep going like this. Now I want you to see something. What if we want to draw the average current of this shape? How would it look? So a good point is this point, and another point is this one, another one is this one, this one, this one, this one. We can see that all of them lie on a straight line. You see how cool it is? They almost lie on a straight line. You know, this one has to be here, right? So what is the slope of this current? You know, when we had constant 5 volts, we had a constant slope of 5 amps per second. Like this, when we switched the inductor to the 5 volts and kept it on the 5 volts. And this was really bad. Now when we kept switching 5 volts, 0 volts, 5 volts, 0 volts, and so on, the inductor current is still increasing, but it is not increasing like that. If we just switched it to 5 volts, it would keep growing at 5 amps per second. But that's not what it did. It's actually growing at a rate 2.5 amps per second, this average value. You see, geometrically, after 2 seconds, it reached 5 volts. You see, it was here. It increased 5 volts, which means it went up 2 small squares like this at this point. So this is the time that it went from some value to some other value plus 5 volts. So this time is 2 seconds. This is from here to this is 1 second. This is another second. So 2 seconds. So 5 over 2 is 2.5. You know, geometrically it would give 2.5 ampere per second. So what I want to say is, when we had an average value for the voltage equal to 5 volts, we got an average value for the slope of 5 amps. When we had an average value of 2.5 volts, we had an average value for the slope of 2.5 amps per second. So this means that the average voltage across the inductor equals, or at least proportional to, the average slope of current through the inductor. We can write it mathematically like this: the average inductor voltage equals L times the rate of change of the average inductor current. Right? So, if we want to have constant inductor current, we need this thing to be 0. You know, if something is constant, its rate of change is 0. So for constant average current, we need 0 average voltage, right? So for constant average inductor current, we need 0 average inductor voltage. So this takes us to the average steady state definition. We say that average steady state is the state at which everything is constant on average. So inductor current is constant on average, right? Remember, on average. So inductor current is constant on average, which means the inductor average voltage is 0. So for example, if we make circuitry like this, we have inductor right there, right? This is 5 volts and this is negative 5 volts, but it, switched polarity or reversed polarity. So if we keep switching between these guys, right, meaning the voltage across this inductor, which is 1 Henry, of course, the voltage across this inductor looks like this. Time voltage. The voltage across the inductor is 5 volts in the beginning and switched to negative 5 volts for another 1 second, and again positive 5 volts, and again negative 5 volts, and so on. So this is 5, this is negative 5. So here the average voltage is 0, or if we would like to, alright, so the average voltage right here is 0, which means that the inductor current would look like this. Integrating that guy, we get an increasing current, then a decreasing current, and then increasing again, decreasing again, increasing again, and decreasing again, and so on. So we get a constant average current value of 2.5 amps across this inductor. Right? So that's it for today. And if we increase the switching frequency, this ripple decreases, or this ripple becomes faster, right? So that's probably most of the important things that we need to know about inductors, so to summarize, golden rules, write these ones. So inductors resist instant current changes because V equals LdI by dt, because this voltage cannot be infinite. Second golden rule. Unless or while VL equals some positive value, IL is increasing, so which means don't keep inductor connected to DC voltage, because this is bad. Third golden rule, on average steady state, and this is the most important one, the average voltage of the inductor equals 0. This is the most important one in power electronics, in all of power electronics, not just DC-DC converters or switching power supplies. So this is the most important reality about inductors. The average voltage across the inductor is 0. That's most of what we wanted to say today. Probably all of it. Goodbye.